In this video, we will talk about dividing polynomials using polynomial long division and synthetic division. First, let's talk about the division algorithm, which says if p of x and d of x are polynomials where d of x is not equal to 0, then there exists unique polynomials q of x and r of x, where r of x is either 0 or of degree less than the degree of d of x, such that we can write in form 1, p of x over d of x is equal to q of x plus r of x over d of x. And form 2 says p of x is equal to d of x times q of x plus r of x. So let's talk about long division. And you might need a refresher how to do long division with numbers so that we can talk about long division with polynomials. So example 1 says write 21 divided by form in the two forms shown in the division algorithm. So I'm going to go ahead and I'm going to do some division of these numbers. 4 goes into 21 5 times. That leaves us with 20. And then 21 minus 20 is 1. Now that represents our remainder because there's no more numbers to bring down. So our remainder is 1. Now if we were to write this in form 1, if we were to replicate this form 1 here, we would say 21 over 4 is equal to 5 plus our remainder, which in this case is 1, over our divisor, which in this case was 4. And really that's the same thing as a mixed number. This is the same thing as the mixed number 5 and 1/4. So this is all basically form 1. Now for form 2, the way that you get form 2 is that notice if I were to clear the denominator here, if I multiplied every term by d of x, what's going to happen is this will cancel with this, it will also cancel with this, and then I will have to multiply q of x times d of x, and so that is how we get p of x equals d of x times q of x plus r of x. So form 2, you get it by multiplying the entire equation by your divisor. So I'm going to go ahead and erase this, and we can see here that if I multiply everything by 4, then form 2 is going to tell us that 21 is equal to 4 times 5 plus 1. And so here's our answer for form 2. I'm going to go ahead and erase this. And those are our two forms. Example 2 says divide 240,395 by 3 and write your answer as a mixed number. So I want to know how many times this goes in here. All right, so first we ask how many times does 3 go into 2? And 3 is larger than 2, so that's going to go in 0 times. And then we can look at the next number. 3 goes into 24 8 times. So now I'm going to subtract off 24 because 3 times 8 is 24. That's going to leave me with 0, and then I'm going to bring down this next digit. 3 goes into 0 0 times. That's going to give me 0. 0 minus 0 is 0. And then I'm going to bring down this digit, so I have a 3. Now I want to know how many times does 3 go into 3. That happens 1 time, so I'm going to put a 1 here. And then 3 times 3 is 3. So I have 0. Now I'm going to bring down this 9, and I ask how many times does 3 go into 9? That happens 3 times. That's going to leave me with 9 minus 9, which is 0. And then I'm going to bring down this 5. And then 3 goes into 5 1 time. And then I'm running out of space, so I'm going to do 5 minus 3 times 1 is 3. And that's going to leave me with 2. There's no more digits to bring down, so I know that I would stop there, and 2 represents my remainder. So now we're going to write our answer as a mixed number. I can go ahead and drop the leading 0. So my answer is 80,131, and then we're writing it as a mixed number, so my remainder is 2, and my original divisor was 3. So this is our mixed number. Now the notation for a mixed number is kind of interesting because when I have a whole number and a fraction, normally when I put those next to each other, that indicates multiplication, but that's not what's happening here. Really, this is like form 1 of the division algorithm. It's really 80,131 plus the remainder over the divisor. So it's kind of like that. And then really I should also include the original numbers. So if I'm writing form 1 of the division algorithm, it would say 240,395 over 3 is equal to this thing. All right, so let's move on to doing long division for polynomials. Example 3 says divide 6x cubed plus x squared minus 12x plus 5 by 3x minus 4 and write your answer in both forms from the division algorithm. So just like we did when we were doing long division with numbers, I'm going to put my divisor on the outside of my division bar, and on the inside I'm going to put 6x cubed plus x squared minus 12x plus 5. And it's going to work very similarly. So I want to start off and ask myself, what can I multiply to 3x that would give me 6x cubed? And we would multiply 2x squared to 3x. So now I'm going to put a minus sign and a set of parentheses. Now 2x squared times 3x is 6x cubed. And then now what I want to do is I want to multiply 2x squared times negative 4, and that's going to go in that empty spot. So if I multiply those, that's going to give me minus 8x squared. And now I just subtract vertically. So I have 6x cubed minus 6x cubed. That gives me 0. Then I have x squared minus negative 8x squared. And that is going to give me positive 9x squared. Then I'm going to go ahead and drop this down. So I have minus 12x. I'm also going to just drop my 0. So now what I want to do is I want to ask myself, what do I need to multiply to 3x so that I will end up getting 9x squared? And the thing that accomplishes that for us is going to be positive 3x. So 3x times 3x is 9x squared, and then I'm going to multiply 3x times negative 4, which is negative 12x. So 9x squared minus 9x squared is 0. Negative 12x minus negative 12x is also 0. And then I'm going to go ahead and bring down my positive 5 here. So I can really just get rid of the zeros, and I'm just left with 5. And I know that I need to stop at this point because the thing that we're left over with is now, it has a degree that is lower than our original divisor. So that's how I know to stop. So again, 5 represents our remainder. Now let's go ahead and write this in form 1 of the division algorithm. So we're going to start off with our original polynomial, 6x cubed plus x squared minus 12x plus 5, and we are dividing this by 3x minus 4, and the quotient is the answer that we found here. So that's going to be 2x squared plus 3x, and then plus our remainder, which is 5, over our original divisor, which is 3x minus 4. So here is our form 1 final answer from the division algorithm. Now, coming down here, I'm going to write form 2. And again, remember, we gain form 2 by just getting rid of all the fractions or using the method of clearing fractions. So if we do that, we're going to get 6x cubed plus x squared minus 12x plus 5 is equal to 3x minus 4 times 2x squared plus 3x, and then plus 5. So there's our final answer for form 2, and that completes this example. Example 4 says divide 2x to the 5th plus x cubed minus 2x squared plus 3x minus 5 by x squared minus 3x plus 1, and write your final answer in both forms from the division algorithm. So on the outside, I'm going to put x squared minus 3x plus 1. And on the inside, I'm going to put 2x to the 5th. Now, notice that if we're going in order of powers as they are descending, we're actually missing the quartic term. So I'm going to use a placeholder, and I'm going to put plus 0x to the 4th power, and then continue on. Then we have plus x cubed minus 2x squared plus 3x minus 5. All right, so just like last time, I'm going to ask myself, what do I need to multiply to x squared so that I'm going to get 2x to the 5th power? And the coefficient will be 2, and then if I multiply x squared times x cubed, that would give me a 5th power. So now I'm going to go ahead and multiply 2x cubed times each of these terms. So let's do 2x cubed times x squared is 2x to the 5th. Then I'm going to do 2x cubed times negative 3x. That's going to give me negative 6x to the 4th power. And then if I multiply it times 1, that's going to give me plus 2x cubed. Now I'm going to close off my parentheses, and I'm going to subtract vertically. 2x to the 5th minus 2x to the 5th is 0. 0x to the 4th minus negative 6x to the 4th is positive 6x to the 4th. And then x cubed minus 2x cubed is a negative x cubed. Now I'm going to go ahead and drop down this term. I'm also going to get rid of the 0 again. Doesn't make a difference there. Okay, so now we want to ask ourselves, what do I multiply to x squared that is going to give me 6x to the 4th power? So I'm going to need a positive 6, and then I'm also going to need an x squared. Now I'm going to take 6x squared and multiply it to each of these terms. Okay, so now we can subtract vertically, so this is going to give me 0. Negative x cubed minus negative 18x cubed is plus 17x cubed, and then negative 2x squared minus 6x squared is going to be minus 8x squared. All right, so now I'm going to drop this 3x down, and that's going to be plus 3x here. Do I need to stop at this point? Well, the thing that I'm left with, 17x cubed minus 8x squared plus 3x, has a degree of 3, or is a cubic polynomial. Our original divisor has a degree of 2, so since what we have as remaining is not less than the degree of the divisor, we keep going. So now I want to know, what can I multiply to x squared? That's going to give me 17x cubed. So that looks like it's going to be plus 17x. So now I'm going to take 17x, multiply it to each of these terms. That's going to give me 17x cubed minus 51x squared, and then plus 17x. So now I'm going to go ahead and subtract vertically. This is going to give me 0. Negative 8x squared minus negative 51x squared. That's going to give us positive 43x squared. And then 3x minus 17x should be negative 14x. And then I'm going to go ahead and bring down this minus 5. Again, I can just drop the leading 0 there because it does not make a difference. Now, the thing we have remaining is a quadratic, and our divisor is also a quadratic, so it's still not a degree that's less than the divisor, so we would still keep going. So at this point, I ask myself, what can I multiply to x squared? That is going to give me 43x squared. And so that is plus 43. All right, I went ahead and filled in the next two. Now I'm going to subtract 43x squared minus 43x squared is 0. Then we have negative 14x minus negative 129x. All right, so after subtracting and fixing a quick error that I had, your remainder should be 115x minus 48. So this thing is our quotient. This is our divisor. This is our remainder. And now let's take these pieces and write our solution in the two forms of the division algorithm. I forgot to mention that this thing is called the dividend. So now let's go ahead and put all of these pieces together. All right, so here is form 1 from our division algorithm. Let's go ahead and get form 2. And remember, we're going to get form 2 by using the method of clearing fractions and multiplying every term by our divisor, which in this case is x squared minus 3x plus 1. So I'm going to go ahead and quickly write that out. All right, and here is form 2 using the division algorithm. Next up, we are going to talk about synthetic division, which is, in my opinion, a lot easier than having to rely on polynomial long division. The downfall of synthetic division is that we don't always have the capability of using it. So let's talk about it. Synthetic division is an alternative way to divide polynomials, but it only works when the divisor is of the form x minus c. So let's put it to use. Example 5 says, find the quotient and remainder using synthetic division. So we have our numerator here, x cubed minus 10x squared plus 20x plus 30, and we're wanting to divide that by x minus 6, which x minus 6 is of the form x minus c, so we're okay to use synthetic division. Now, when you have your denominator or your divisor, you want to solve it for its 0 or root. In other words, you set the denominator equal to 0 and solve for x, and so we get x equals 6. So our 0 or root of our denominator is 6, so I'm going to write 6. And then I'm going to make this, it almost looks like the long division box, but it's upside down and a little bit longer. And inside the box, in this top row here, I'm going to place the coefficients of my numerator polynomial. So, and I want to place my coefficients assuming that all of the terms are in order of their descending degrees. In other words, I want the highest degree first, and then going down to the lowest degree. So reading this off, my coefficients of the first term are 1, and then moving on, we have negative 10, 20, and 30. Okay, so now the way that synthetic division works is inside of our box, we add vertically. So 1 plus nothing is 1. So I'm just going to put a 1 down here. And then from there, we multiply diagonally. So 6 and 1, I want to multiply those two numbers together. That's going to give me 6. And now we kind of just repeat that pattern. We're going to add vertically, so negative 10 plus 6 is negative 4. And we're going to multiply diagonally. So now I want to multiply 6 times negative 4, which is negative 24. So now I want to add vertically, so 20 plus negative 24 is negative 4. And then once again, I want to multiply diagonally, so I'm going to multiply 6 times negative 4. That gives me negative 24. And then adding vertically gives us 6. So we stop here. Okay, so the bottom row here outside of our box helps us to get our answer. So the very last number in the last column always represents the remainder. And the remaining numbers, these represent the coefficients of our quotient. And because we have our remainder here, I always tell my students to start off in the last column on the right. So that's my remainder. So I'm just going to put R for remainder. This represents the coefficient of my constant term. This represents the coefficient of my linear term. And this represents the coefficient of the quadratic term. So essentially what's happening is, as you start from right to left, the degree of each of these terms is increasing by 1. So this is going to be the coefficient of x, this is going to be the coefficient of x squared, and if there were more numbers that we could choose from, then the next term would be the cubic term, and then the quartic term, and so on. And so you keep going by increasing the power by 1. So I'm going to go ahead and erase some of this. Okay, so let's go ahead and write out our quotient. Okay, so our quotient is 1x squared minus 4x minus 4. So I'm just pulling these. These represent my coefficients for my quotient, and I'm pulling them down here. And really 1x squared is the same thing as x squared, so I could just erase that part. So here is my quotient, and then again, the remainder, we have it kind of highlighted here, is 6. So there's our completed answer for part A. All right, so if I were to solve for the 0 in the denominator in part B, my outside would be -3. And then I need to place my coefficients. So the first one is 1. And now notice this is a cubic term. My next term should be quadratic, but there's no x squared term. Or another way to think about it is that the coefficient of x squared is 0, kind of like we had earlier when we were putting a placeholder for inside of our long division bar. Our next coefficient is -8, and then our last coefficient is 2. So I'm going to add vertically. 1 plus nothing is 1. Then I'm going to multiply diagonally. -3 times 1 is -3. I'm going to add vertically. So 0 plus -3 is -3. And then if I multiply diagonally, we get 9. Then -8 plus 9 is +1. And multiplying diagonally, -3 times 1 is -3. And lastly, adding vertically, 2 plus -3 is -1. And remember, this thing represents our remainder. So let's talk about our quotient, which is our first. So this is going to be constant. This is going to be linear, and this is going to be quadratic. So it's going to be 1x squared minus 3x plus 1, and then our remainder is -1. In example 6, we want to find the quotient or remainder using synthetic division, just like we did in the previous example. And in these, I'm going to move a little bit quicker. Okay, so I'm going to add vertically, multiply, add vertically, multiply, add vertically, multiply, add vertically, multiply, and add vertically. So 12 represents my remainder. This represents my constant term. This represents my linear term, my quadratic term, and this is my cubic term. So that means that our quotient is x cubed plus x squared plus 3x plus 5, and then our remainder is 12. All right, so for this next one, I'm going to write -2 on the outside since that's the 0 of my denominator, and then my coefficients of the numerator are 1, 2, -9, and -18. So I'm going to add vertically, multiply, add vertically, multiply, add vertically, multiply, and add vertically. Oh, look! This is the first time that we've run into when we've divided polynomials where our remainder has been 0. what does this mean? Well, if I were to write this in form 1, then this represents my constant term, this represents the coefficient of x, and this represents the coefficient of x squared. So that means that when we divide, we get a quotient of x squared minus 9. And then, again, if we were writing this in form 1, we would say plus 0 over x plus 2. But 0 divided by x plus 2 is just 0, so really I can just erase this. So it turns out that when I divide that cubic polynomial in the numerator by x plus 2, I get another polynomial and no remainder. So when I divide this polynomial by x plus 2, we get x squared minus 9 with no remainder. And this is really important because now what we can do at this stage, since there's no remainder, if I took this equation and I multiplied both sides by x plus 2, on the left-hand side, it's going to get rid of my denominator, and then I can go ahead and drop my brackets or parentheses, and then we'd have x squared minus 9 times x plus 2 on the right-hand side. Well, what did we just do here, essentially? What we did was we took our cubic polynomial that we started with, x cubed plus 2x squared minus 9x minus 18, and we started to put it into factored form. So we could rewrite this as x squared minus 9 times x plus 2. Now, is this completely factored? It is not, and we can continue to factor it. But this thing here, x squared minus 9, that thing is a quadratic, and if I were to use the x method on it, I would be searching for two numbers that add to 0 and multiply to negative 9, and those numbers are 3 and negative 3. You can also, or might recognize, that this is a special case called a difference of squares. So it could factor that way as well. So now what we've done is we've taken this cubic polynomial and we've factored it into 3 different linear terms that are being multiplied together. Now, you might be asking yourself, why would we care to put a polynomial into factored form? If you said to find the x-intercepts or to find the zeros of the polynomial, you would be absolutely correct. So now that we've factored this, I can set this equal to 0 and use the zero product principle on this. And if I set each of the linear factors equal to 0, we would find that the zeros of our original cubic polynomial would be negative 3, positive 3, and negative 2. Now, why do we care about the zeros or the x-intercepts? Well, along with the end behavior, this is going to help us to visualize a graph of this function. So now that we got all of that excitement out of the way, let's go ahead and finally answer the question. We are going to identify the quotient, which was x squared minus 9. And then our remainder, after we did synthetic division, we ended up getting 0. So here is our final answer for part B. So let's talk about these two theorems. The remainder theorem says if the polynomial p of x is divided by x minus c, then the remainder is the value p of c. Very interesting. The factor theorem says c is a zero of a polynomial function p of x if and only if x minus c is a factor of p of x. So I just want to highlight, this is not a misspelled if. If it has two f's, it means if and only if. So let's put this to use. In example 7, it says let p of x equal x cubed minus 7x plus 6. Show that p of 1 is equal to 0 and use that information to factor p of x completely. So let's go ahead and evaluate p of 1. I'm going to take 1 and plug it into my function. So I'm going to have 1 quantity cubed minus 7 times 1 plus 6. I want to go ahead and simplify this. 1 cubed is 1. 7 times 1, that's going to give us minus 7, and then plus 6. 1 minus 7 is negative 6, plus positive 6 is going to end up equaling 0. So we accomplished the first part where it says show that p of 1 is equal to 0. We did that. I'm just going to put a check mark. And use that information to factor p of x completely. So we just evaluated p of 1 in this example, which is going to tell us that x minus 1 is x minus c. And what this says is that if we divide our original polynomial by x minus 1, then the remainder is the value of p of 1, which we just said was 0. So that's going to be really nice because then that's going to help us factor it. Because now we know that p of x can be rewritten, let's just write it as we originally had it, x cubed minus 7x plus 6. And this is going to be equal to x minus 1 times some other polynomial. And it's going to be a lower degree polynomial than our cubic, so that when we multiply together, we get a cubic. So how do we figure out what that polynomial is? Well, we're going to use division. And I'm going to use synthetic division. So on the outside of my box, I'm going to put a 1, and then I'm going to place my coefficients, which are 1. Now, this is missing an x squared term, so I'm going to put 0 for x squared, negative 7, and positive 6. Now, I'm going to add vertically, multiply, add vertically, multiply, add vertically, multiply, add vertically. So 0 is our remainder here. And this mystery polynomial that we have is given by these coefficients. So this is going to turn into x squared plus x minus 6. And oh, look at that. That is just a quadratic that we should be able to factor using the x method. So using the x method, I'm going to place my b value on the top and a times c on the bottom. And I want to search for two numbers that add to b and multiply to a times c. And those two numbers are going to be 3 and negative 2. So now what we can do is we can factor our polynomial p of x into x minus 1, and then we said it was x squared plus x minus 6. However, we just factored that quadratic, so I'm going to go ahead and erase that, and we broke it down even further into x plus 3 times x minus 2. So this is the completely factored form of our original polynomial. Now again, why do we care about the completely factored form? From here, it'd be very easy to set this equal to 0 and solve for the x-intercepts or the zeros of my polynomial, and then that would in turn help me to graph this function. That completes this video on dividing polynomials.